This is Neil Patwari. This is ESE 471, and I'm going to talk in this segment about binary FSK, the non-coherent receiver case. We're going to be talking about this block. We had previously talked about the coherent receiver, but now what we're going to do is we're going to talk about what happens when you don't know the phase. This phase of the received signal, when I send a cosine at omega naught t, and when I send a cosine at omega 1 t, this phase is unknown. And so when you build a coherent receiver, you need to have a way to estimate this phase for each frequency in the FSK system. For binary FSK system, we'd need two phase-locked loops that would track what the phase is of the signal when frequency 1 and frequency 0 is sent. This can be somewhat complicated, especially because half of the time the signal is not being sent. And so the phase lock loop needs to take that into account and not try to search for the phase while the opposite frequency is being sent. In the non-coherent receiver, I don't try to match my phase to the phase of the received signal. I simply note that a cosine at any phase can be represented as I and Q components, where there is some linear combination of cosine and sine in the signal at any time. So what I do instead is I correlate my received signal with the cosine and the sine both at the frequency omega naught. Okay, so here's my first part of the signal. I'm correlating with cosine and sine. And my second part of my signal at omega 1 is correlating with the cosine and the sine at omega 1. And what I do after running my correlation receiver or my match filter receiver, I sample, I square the cosine and the sine part, and that gives me the magnitude squared. If these are I and Q components, then what I get is the magnitude squared. In the Proakis and Salehi book, it goes through a derivation to describe the probability of error in the non-coherent receiver case. So what it does is it sets up the problem. So under H naught, we're sending the signal A0, which is this vector 1 of the phi0 component, 0 of the phi0 component. And I'm going to add noise to that, and that becomes my received signal. My received signal becomes this vector of the 1, 0 plus noise. And my H1 case, my received signal is the opposite. It's 0 and 1. Plus noise. What is hard to see here is that this two-dimensional problem turns into a four-dimensional problem where I'm measuring this vector R, which is all four components, R0C, R0S. These are from these top two components. And then R1C and R1S. These four components make up this vector at our decision. Well, at this point in the receiver. And what these components are, the distribution of these are all Gaussian. The R0C and the R0S, they're going to be Gaussian under H naught, but with a amplitude, with a magnitude of 1. So if I could look at just the R0C and R0S component, there is some amplitude, and here I'll switch colors, there's some amplitude 1 in some direction because we're not matching, well, it's at this phase, phi 0 is what I've called it, unfortunately, because that phase is the same name I used to describe the orthogonal waveform, but just bear with me while I call it an angle. And the mean of the received signal is this magnitude but the distribution around that magnitude is Gaussian. So I have these Gaussian bell-shaped curve coming out of the whiteboard centered at that point. On the other hand, the R1C and R1S under the case of H naught this is, under the case of H naught, I've sent none of the frequency omega 1. So in this case, the center of the signal is here at 0 because I have not sent any of the omega 1 frequency. So whatever I receive out of these components is noise. It's still going to be Gaussian because the noise is Gaussian, but this bell that sticks out of the whiteboard is centered at 0 at the origin. And so we're going to get some point in this 4-dimensional space, and we're going to have to decide which frequency was sent. And we're going to decide which frequency was sent by figuring out our measurement. Our measurement is going to be at some point, and we're going to figure out how far away it is from the origin. And we could, if I could draw 4 dimensions, I would, but for this case, I'm drawing 2 sets of 2 dimensions. And we're going to find out which component has higher amplitude, or higher squared amplitude in this case. It doesn't really matter if I look for the higher amplitude or the higher squared amplitude. So the squared magnitude here would be R0 squared. It's going to be R0C squared plus R0S squared, and the magnitude squared here, R1 squared, is going to be R1C squared plus R1S squared. And from R0 and R1 squared, I'm going to figure out which is higher. If R0 squared is greater than R1 squared, then I'm receiving more energy and frequency 0, so I'm going to decide H0. And if R0 is less than R1 squared, I'm going to decide H1. If you study the statistics of this and you do this integral that you need to do here, well, you'd find, as Proakis and Salehi show, that the probability of error takes this form. It actually becomes, it gets very computationally challenging, but in the end, the probability of error expression is quite simple. It says that we take the EB over N naught and divide it by 2, the negative of that, and take the exponential and multiply by 1/2. And that's our probability of bit error, or equivalently the probability of symbol error in binary FSK. So I highly recommend reading through that derivation if you're interested, but the result is that for non-coherent binary FSK, this is how we calculate the probability of bit error. In terms of comparing the performance of non-coherent binary FSK and coherent FSK, the binary FSK is going to have a slightly worse performance. It's something that we will graph and show in an upcoming segment.